Computerized control diagnostic overview 2. It says determine the relative importance of display scan to data. Okay, the ECM serial data transmitted to scan to may have a data list of 50 or more items. That's what you don't need. On a scan tool, basically all you're looking at is the most important items. Even when ASE gives you a snapshot of something, you're looking at the most important items on the test. On the scan data on the ASE test. Not all items on serial data are relevant. Right? To make the data transmission faster, all you gotta do is customize the scan tools. I recommend that to everybody in class. A system voltage, the battery and charging system must provide a continuous regulated voltage to 12 to 14 volts. More importantly, the ECM must receive the voltage. Okay, so if you lose voltage to the PCM, it can obviously turn the car down, even in the composite vehicle. We're going to look at it later on, but certain pins that have to receive voltage all the time. When we get to the composite vehicle, I'll show you which ones they are. Most serial data streams provide a reading system voltage at the ECM. Most serial data streams provide a reading system voltage at the ECM. It must be within a normal range of the ECM and all sensor components to be operating properly. So in other words, you got a charging system problem with the SAN, right? The ECM is going to give erroneous signals out to the actuators or drivability problems. So system voltage to that, I think it's keep a lot of memory and a power supply to it. It's essential. Alright, engine speed and RPM. Engine RPM are tach signal is the signal most important input to the ECM. Without the RPM signal, the ECM cannot tell the engine is even running. Remember, that's one of the important signals we talk about too. When we talk about customizing scan tool, it's the RPM signal. Remember, if you lose that, you'll usually lose the spark, fuel pump, and injector trigger. So they talk about if they give you on the test something about a car won't start or acting erratic. Okay, because remember, it's saying here it will lose the signal. If you lose the signal to the PCM, it won't start. But if you get an erratic signal to the PCM, or ECM I should say, for the ASE composite vehicle, it will cut out, right? Like a misfire, a surge. Because remember, when that signal goes away, the computer's going to turn off. So, for instance, if I get a bad RPM signal that's cutting out, cause maybe a chipped tooth or a erratic RPM input, the PCM is going to respond to that input and cause the car either hesitate or cut out. So this is saying that it won't start, but if I get an erratic signal also, it's going to have a problem. The tach signal tells the ECM whether the engine is cranking, idling, acceleration, deceleration, right, or cruising. So basically, like here's a good example. All right, you get an RPM signal into the PCM. Where's my thing at? All right, here you get a nice RPM signal into the PCM at idle. Right, and the car is idling fine. On acceleration, the same signal does this. Erratic signal, right? That signal is going to affect the way the PCM trigger the injectors and fuel pump and spark. Now you're going to have a car that's going to cut out. This is what I mean by erratic signal. Yeah, because it doesn't recognize that signal at all. It only sees ones and zeros. It got to be a nice, clean digital signal. You can't see anything like that.
Symmetrical pattern.
Yeah, a nice, clean pattern like this.
The only time that it varies is when it hits the 10 or whatever.
The only thing that's going to vary is the frequency. How many times it turn on per second? The height, the height, and ground size should be fixed. But the dimension may change because of the increased RPM. But it shouldn't be like this. 1 minute is like this, then it's like this. Right? It shouldn't do nothing like that. That's erratic. That's gonna cause a problem. You lose that signal, right? The way the computer is gonna trigger the injectors, the fuel pump, control the fuel pump, and spark is gonna be affected. Right? This is saying it may not start, right? But can also cause a surge or a misfire. Alright, also. So you gotta keep that in mind too, because if it loses that signal, or if the signal is erratic, it's going to cause a drawability issue also. The tach signal or RPM signal affects ignition, fuel, emissions, and the transmission. Alright, the way it's shifting. Because remember, the ECM gives an output signal to the transmission solenoids.
So how would it affect the trend? Is that
Because remember, if you're given a higher RPM, that's a good question. If you're getting the car, you step on the gas pedal, the vehicle speed increases, the RPM increases. All of a sudden, the RPM signal goes from a nice clean, let's say 4K hertz or 4,000 hertz, drop down to 600 hertz. The signal drops out. To the computer, it thinks you turned the key off. So, decelerating. If it does that, it's going to downshift the transmission. Or turn off the injectors on a lean mode. Put the injectors in a decel mode when you're really not. Remember, when RPM increases, it's a command to the PCM for more fuel. As soon as the PCM/ECM sees a decrease in that signal or that frequency signal, it thinks you're letting off the gas pedal or turning the car off. So it's going to respond to that. Remember, the ECM does not know what's going on in the physical world. It has to see an input signal. So if that input signal is erratic, it's going to respond with that signal. But for example, if I'm giving it gas from a stop, take off into the freeway, it's going to see an increased vehicle speed. It's going to see an increase in RPM, right? Indicating that you need more fuel. Shift the transmission. But if all of a sudden that same signal cuts out or dies down or go away, either way you want to put it, it's going to say, okay, they decelerating or they turn the car off. So it's going to respond with that. It's going to decrease the injector pulses. It's going to downshift the transmission, and that's when the customer complains about, oh, my car's cutting out or has a misfire. It's really a poor input into the PCM/ECM causing that, because it's following the signal. See, all these signals right here, the RPM signal and the tach signal, are inputs to the PCM/ECM, telling the ECM what to do. If it doesn't see that signal, it's going to respond to that signal. That makes sense?
Yeah. So how does it affect emissions?
Oh, let's say that let's say you have to start the misfire. Right, the emissions are going to go up. Or if it's shifting incorrectly, NOx might go up. Right here it says vehicle speed are miles per hour. Vehicle speed affects transmission control, ignition timing, and fuel metering. That's a vehicle speed sensor. It's the same effect. You have a vehicle speed sensor go out, saying you're going 60 miles an hour. The vehicle speed sensor tells the computer to shift the transmission and apply the right amount of fuel. All right. But if that vehicle speed sensor says you're decelerating and you're not because it has a glitch, the computer's going to decelerate, downshift the transmission again. Right? It's going to downshift the transmission. It's going to change the timing, and it might go in decel control, which means turn off the injectors. So remember this: when you let off the gas pedal, that's decel. It leans out the air fuel mixture. So if you're driving down the street and a vehicle speed sensor goes away or glitches, it thinks you let off the gas pedal. It's going to go in decel mode, lean out the mixture. It's going to downshift the transmission, right? And it's going to lean out the fuel mixture. And that's when the car starts surging or cutting out. Now here's the other thing. Most vehicle speed sensors, right, could be a permanent magnet, which is like this. That's a bad drawing. Something like that. And the height of that signal is important too. So if I think it's like 3 volts AC. As RPM increases, it gets bigger. If it's an AC signal, right? So if that signal gets weak or the magnet becomes weak, it affects the transmission timing, and fuel also because of a weak magnet. This is especially on the ASE test. They usually ask this for the RPM signal too, because the RPM signal could be a permanent magnet or a digital signal. If it's a permanent magnet, the height of the signal is important. And you can see here it also affects cruise control and ABS operation. Temperature parameters: the temperature of the engine coolant intake, transmission fluid. Transmission fluid affects the fuel, ignition, and emission system operation, as well as the transmission control. Right? Remember, it has to let the vehicle know, the computer know the car is at operating temperature. Manifold pressure sensor, or vacuum barrel pressure. Now, if it has a map sensor on there, it's usually a barrel sensor also. And usually reads the barrel. This is, say if it's a digital signal. Analog works the same way also. Analog DC voltage. This is one event. And let's say that this is supposed to be 159 hertz. Right now I'm just talking about barrel. That's key on engine knob. I want to see 159 hertz for the atmospheric pressure. That's where your initial pulse width is going to start from for the injectors. That's your altitude. If this thing wasn't at 159, was at 85 hertz, you can have a car running lean and have a lean hesitation. So this reading with the key on engine knob is important also, because that's your initial pulse width to get the car started. That's one of the inputs to get it started. Guys, this tells the computer what altitude you're at. So if this is off, I'm gonna have a car run lean. Right? It's gonna be a lean hesitation or a NOx emission or a NOx increase. Inches of mercury like vacuum. This is a this is the car. On this case here, the car's not even running, because when the car is off is 0. Inches of mercury would be 0, because the car's not running right now. This is key on engine off. There's no vacuum on this at all.
So that's what's telling you there's no vacuum.
Right. This is reading this is just reading the frequency off that sensor. Key on engine off the barrel sensor. Remember, the barrel sensor has no vacuum lines hooked up to it. It just reads atmospheric pressure.
That's it.
And later on on the ASE test booklet, they have a conversion chart we could go through also. You can look at the way it transfer from compare mercury to pressure. But this has no vacuum readings on it at all. Okay, it's just reading atmosphere. It has no vacuum readings. It's just reading atmospheric pressure only. I'm talking about the barrel. Now once it starts up, oops, get this out the way.
Well, the barrel is basically for timing purposes, I imagine.
That's for what?
Timing purposes? So to time the spark, the ignition.
All of it's for timing. Barrel, map,
Right?
all that specs timing. Barrel is basically for your altitude.
Mm-hmm. That's basically all it does, right?
Yeah, it's tells the computer you're at sea level or up in the mountains somewhere.
Gotcha.
That's your barrel pressure. Because remember, as you go up in altitude, the air gets thinner. So you gotta change the fuel delivery
Yes.
based off at sea level. It's a different fuel delivery. Now in this case here, when it's running, you got more pressure in the manifold. Now the car is running, and your map sensor is your pressure sensor. And if the car is running, you should see like 18 to 21 inches, 22 inches of mercury. All right, you have high vacuum, low pressure. As you step on it, the pressure increases and the vacuum decreases. Increase in pressure indicates to the PCM/ECM and needs more fuel. Okay, so my pressure increases from the manifold pressure sensor. It tells the ECM you need more fuel. And that's also your load sensor. Now, on some cases, it's going to tell you in the composite vehicle that the map sensor, actually, I hope I remember that when we get to that part, because this is a trick on the ASE test, that that they use the MAP sensor. If I remember correctly, it has a mass airflow and MAP sensor. The MAP sensor the MAP sensor is used as a backup or for a monitoring purposes. The mass airflow sensor is the input for the load. The MAP is a backup for the mass airflow.
The what?
The MAP sensor is a backup for the mass airflow sensor. If the mass airflow goes out, they're going to use the readings from the MAP sensor in limp mode. Mass airflow is the load input signal. So these air pressure parameters are primary inputs for fuel and ignition, control, and transmission shifting. Most control systems use air pressure measurements as a starting point. So as I said earlier, it's a starting point, right? Air pressure measurement as a starting point for the ECM to calculate the relative engine load and your fuel delivery. So key on engine off, they're going to use the barrel. They're going to start from that, whatever that barrel reading is. So if that's off, the whole fuel delivery is going to be off. Any given symptom or driver complaint can be caused by a problem in more than one system. A problem can appear to be based on one system when in fact it originates in another. Here's an example. A longer than normal fuel injector pulse width and higher long-term fuel trim correction factors are fuel system symptoms, but their cause can lie in several other engine subsystems. Like for example, what do you think? If I have a longer than normal injector pulse width and a higher fuel trim, what do you think could cause that?
Oh, it can be the map. I mean, the map can be off. It could be telling a different rating.
Now, how do you think that would cause this situation?
So for example, less vacuum means you're accelerating.
Less vacuum means what?
You're accelerating. You're demanding more fuel.
Right. So you're demanding more fuel. Right. Yeah. So a low vacuum is you're under a load. Also, a false lean condition. Say you got like a fuel pump. Right. There's low fuel volume. Or a bad, because of a mechanical problem or fuel filter can cause this. How about a bad ground to the fuel pump connection can cause this. Right. Right. And the O2 system is going to pick up, says I'm running lean, it's going to increase the injector pulse width. A mass airflow sensor, like you're saying, can cause a bad input also. Right? Because the wire is out of calibration or the hot wire is dirty. It could cause this also. But the code may not be for those problems, especially at bad ground. It may be for P0171. It may be for O2 sensor. It may be for something else. It might be for misfire. But the root cause of the problem is in another area. This is what this means here. Like what you said about vacuum, right? A bad vacuum, right, will cause the MAP sensor pressure to change, on voltage to change. You can have a valve timing problem from a valve timing problem that drops the vacuum, and that affects the MAP sensor. Here's one. A mechanical problem such as an intake vacuum leak could be the root cause. On the other hand, an incorrect input signal from a barrel pressure sensor or manifold pressure sensor could cause unusual fuel control symptoms. That's what we discussed earlier. Differentiating between the mechanical problems and computer system problems is part of identifying and repairing the root cause of any symptom. A diagnostic technician must look for abnormal test results to isolate the cause of the problem to one system. And this is what the ASE test is about. When they ask you a question, you gotta isolate that problem by looking at the data. Right? By looking at the data, I'm gonna show you some examples in a second. By looking at the data, you gotta isolate the root cause of the problem. And let's keep in mind the whole test is a diagnostic test to figure out the root cause of each issue. Diagnosing no start, hard starting, installing, engine misfire or poor drivability, incorrect idle speed, poor idle, hesitation, backfire, surging, spark knock, power loss, reduced fuel economy, illuminated mill, and emission problems caused by failures of computerized powertrain controls. A computer that loses power or ground will not function at all and will cause a no-start condition of any fuel-injected engine. We lose ground, we lose power, it can affect the computer. With a failure of the computer control system, it's possible a source of these conditions. If it should not be considered the problem until the basic mechanical and electrical tests have been performed. In other words, you got a car. If the ASE test give you a question that the car will not start, okay, and here's a good one. It tells you that you have a car that will not start, and somewhere in that paragraph you're reading, it doesn't even have 5 volts to a sensor or injected trigger. That may not be a bad PCM. That might be an input problem, like a shorted sensor or a shorted solenoid. Now here, this is how you tell the shorted sensor. If it's a shorted sensor, none of the sensors will have 5 volts to it. That would be a clue. They say no sensor has 5 volts to it, right? Could be a shorted sensor. If I don't have an injected trigger, right? Injected trigger, fuel, or spark, that could be an input to input cause an RPM signal. Also, I can have a shorted solenoid to the PCM/ECM, and the computer's in protection mode and turn off everything. So if they give you a question like that, just don't assume it's a bad computer. Look at the choices they're giving you. And what I like to do is read the question and read the question, read the choices, and start eliminating. All right, until I get down to the 2 best answers. Then I go from there.
Process of elimination.
Yes. Now here's a good example also. A manifold absolute pressure sensor, MAP, will not generate a correct signal if the engine is incapable of producing normal vacuum. Valve timing problems, plugged exhaust system, a collapsed vacuum hose, all can cause this type of situation with the MAP sensor. Now this one, don't forget about this is about the coolant sensor. An output of calibration coolant sensor input can cause hard starting when the engine is both cold and hot. For example, if the coolant sensor has corrosion on the connector, the computer's going to think what? Off the coolant sensor.
It's grounding, meaning it's cold.
Say it again.
It's ground. So if it had a corrosion, I'm assuming it's gonna ground more. And it would think it's cold, right?
Yeah, you're going to think it's a colder car. Right, corrosion on the connector, corrosion on the ground side, corrosion on the power side, open circuit. I think the computer thinks it's a cold car.
Yeah.
Okay, any additional resistance on the coolant sensor, right, it's going to think it's a colder car. So you might have a really hard starting when it's cold or hot. Especially if you have an open circuit. They think it's going to be negative 40 on the scan tool. Yeah, so remember, on the coolant sensor, the PCM is measuring resistance, a voltage drop off resistance. And remember this also. Anytime the computer is measuring a sensor input, it's doing a voltage drop off that sensor. So like in this case here, it's a coolant sensor. The coolant sensor has 2 resistors in the circuit. One is fixed, one is a thermistor. Right? A thermistor means it changes resistance with temperature. So if that coolant sensor had additional resistance on it, the computer's not going to know it. It just sees the additional resistance. So when there's a voltage drop across it, it's going to think it's a colder car because of the additional resistance. Here, for example, let me show you this. I don't know if it's still in the test, because they had one. This is the coolant right here. Let me draw one from the coolant sensor. And here's a coolant sensor here. Okay. Remember, the computer is watching a voltage drop off that second resistor. This is an internal comparator. Our voltmeter. I learned as a comparator. It's watching a voltage drop across this resistor here, based off resistance. And this is a thermistor. It changes resistance with temperature. Any additional resistance on this line from this line through that resistor to ground, it's going to be high. It's going to have a higher voltage drop. And on a thermistor, a higher voltage drop would be a colder car. So if I had corrosion on the connector, which the connector here, colder car. The ground circuit, higher resistance on the ground circuit, colder car. Power side, which is the 5 volts, either here or here, colder car, because of additional resistance. An open circuit, high volts, colder car. That'd be like a -40. So any additional resistance will show a higher voltage drop, and it came to the PCM, it's a colder car. And so I can have a cold start or high emissions. Because remember, now on a colder car, if it's a warm car and they have high emissions, I'm gonna go with this one. If it's a cold car, high emissions, it's gonna add more fuel. Okay, because if I think it's cold, remember on cold cars we run richer. So if the PCM thinks the car is cold, it's going to add fuel to the system, and that's when you have a poor, high emissions and poor gas mileage.
Now, can there be a scenario where if the ECT is failing, the vehicle won't go into closed loop?
Oh yeah, yeah. Because the computer, I think on the composite vehicle, an ASE composite vehicle, it got to see 150 degrees to go in the closed loop. So if it never hits that number, right, and the computer thinks it's cold, it stays in open loop. And again, poor mileage. Yes, you're absolutely right. Now I want to show you this. And last time, this was on one of my ASE tests, and I took it. Now we understand this. You understand this, right? Why it's like this? Okay, now this one may be a little harder to understand. People used to get this one wrong. Oops. All right, here's a TPS signal, okay. Again, I said earlier, usually the PCM, well, not usually, it is. The PCM is doing a voltage drop on the signal wire, which is this wire right here. All right, it's doing a voltage drop on that wire. I have my 5 volts. I have my 5 volts reference voltage feeding the sensor. As the voltage travels through this resistor, it's going to ground. Okay, as it travels to ground, my voltage is going to change. At this point here, I'm gonna have how many volts just going into the sensor? What do you think it's going to be going into the sensor?
4.5.
Huh?
4.5.
Close. Going into the sensor is going to be 5.
Oh, 5.
Going into going to be 5. Now since the voltage is dropping, remember, like I said, the PC on this line is doing the reading of voltage. It's doing a voltage drop. It's reading a voltage drop. Now, since the voltage is going through this resistor here, which is a potentiometer, variable resistor, if I go halfway through it, what you think it's going to see? If I see this right here is a volt. Think this is a voltmeter needle. This is a wiper for the TPS. If that wiper is right in the middle, right? I start at 5 and going halfway through it. I'm gonna see what halfway through this. What would the voltage be here halfway through? Because remember, it's going to drop through this resistor. The voltage is going to drop as it goes through this resistor. So if I get here and it dropped from here, and it already dropped from this point to this point, what do you think it should read in the middle?
2.5.
2.5, exactly. So right here in the middle, I'll probably write 2.5. Now, how about here at the end? Yes, it's going to be near 0. Let's say for a computerized car, 0.1 or less. Right, now understand this. Tell me if you understand this. As that 5 volts go across this resistor, right, it's dropping when it gets closer to ground. It means it's being used up. Now, they usually, on the ASE test, sometimes they ask this question. The PCM sees this voltage drop off this signal wire. It starts from high, starts from here, to wide open throttle, to here, to closed throttle. So it's wide open throttle, closed throttle. Obviously in the middle, we're part throttle. Okay? Now, at a closed throttle, we'll probably will see, say, right now, where we at right now, say 9/10 of a volt. Okay? Right here. If we're reading right here at closed throttle, we might see 9/10 of a volt. In the middle, we'll see about 2.5. And while open throttle, about right here, we probably, like you said earlier, about 4.5. 4.5 volts. All that's telling the PCM the position of the throttle. The voltage is basically telling the PCM the position of the throttle. Now, the question on the ASE test sometimes they ask, I'm going to redo this. Let's say if, on this connector, we had corrosion on the ground side of this circuit. What would that do to this number here?
It would add resistance, so that number would go down.
That is what most people think it will go down. It will go up. It actually will go up. So if I got corrosion there, that 0.9 might be 1.5. It depends on the resistance. The voltage drop will go up. And the reason why, let me get rid of this. And the reason why is because this line right here is doing a voltage drop. It's measuring how much voltage it needs to push the current back to ground. Right? So, if you remember Ohm's law, if I'm in the middle of the 2.5 volts like you said, it requires 2.5 volts of pressure to push the current to ground. If I'm up here and got all this resistance ahead of it, I require 4.5 volts to push the current to ground because I got to push it through all this resistance. If I'm in the middle, I got to push it through this resistance to ground. If I'm down here, I only need about 0.9 volts to push the current through resistance to ground because that's normal. Now if I add resistance to it, now I have this resistor, the normal resistance, plus this. That means I require more voltage or pressure to push the current to ground. So this number goes up.
Gotcha.
You get it?
Yeah. So it needs to supply more voltage to
to push the current through the resistor to ground. Remember, like Ohm's law says, it takes voltage to push current through a resistor. So if I add additional resistance, right, I need more pressure to push the current through it. So it's never going to go up. Because remember, this line right here is doing a voltage drop. So when it's normal, the design resistance, this is normal, all I need is about 9/10 of a volt to go across this resistance here. Let me see that. To go across this resistance here to go to ground. But now if I have an unintentional resistance in the circuit, which is this one, now I got to push voltage, I got to push the current through this and this. In order to do that, I got to increase the voltage requirement to get higher. So that signal line voltage will go up. Does that make sense?
Yeah, it makes sense now.
I drew 12 volts. I drew a light bulb, and I drew this. In a normal circuit, right? In a normal circuit, this will take 12 volts across this load. That would be 12 volts across this load to work that light. So on the input side, I would have 12 volts here. And since this used up 12 volts, on this side, I would have 0.1. Just like on the ground side here, I have 0.1. But now, if I add bad resistance over here, let's say that was 1 ohm, this whole picture changes. Now my whole resistance changes. Now I got 4 amps in this circuit. It's going to be 4 amps in this circuit now. Is that right? Yeah, it's going to be 4 amps in this circuit. I think I did that right, yeah. 1 ohm, so it's going to be 1 ohm here. Oh no, I did that wrong. That's wrong. I got 1 ohm here, 3 ohms here, that's 4. It's 4 ohms in the circuit. Erase that. I know the math didn't come out right. So it's 4 ohms in the circuit. Right, so 4 ohms and 12 volts is now 3 amps. 3 amps in the circuit. Now 3 amps and 3 ohms, instead of 12 volts now, I'm going to have 9 volts. Right? So my voltage drop on this side actually went up. Right? This actually went from 0.1 to 3. Went to 3 volts. And that's how I figured out that it's going to go up. Because now my ground side, instead of being 0.1 like on this side, it increased because I need this voltage to push the current through this resistor to ground. So that same analogy, in my head, the same analogy goes here. If I got resistance here, my voltage here should go up because I need an increased voltage. Just like I need an increased voltage here, I'm going to need an increased voltage to push the current, push the amperage to the resistor that's over here. I don't know if that made sense or not, but this is how I figured that out. Because this, all of a sudden now, my ground circuit voltage just went up. Right, I'm doing a voltage drop right here and it went up. And remember, this is a voltage drop here. And this went up, because of resistance in this circuit. So if I got resistance in this circuit on the ground side, just like I got on this side, my voltage drop also should go up here to push the current through the resistor down line here. To push the current through this resistor, to push the current through any unwanted resistance down line. Because basically this voltmeter here, this signal line here is doing a voltage drop. So any unwanted resistance, my voltage drop is going to be higher to push the current through that resistor, just like this picture down here. You'll see a higher voltage drop on the signal wire because that higher voltage is needed to push the current through the resistors and the unwanted resistance. That's why the
Yeah, so
voltage. That's why that signal wire voltage goes up.
yeah, so it's basically making up for the loss, right? By pushing more current through it.
Yeah, it's yeah, you can say it like that. Yeah, it requires more voltage to push the current through the resistors and unwanted resistance. That's why signal voltage goes up. A MAP sensor, a mass airflow sensor that is out of calibration can cause many different drivability problems on the computer controlled engine because its primary is sensor input, fuel delivery, spark timing, torque converter clutch, lockup can all be affected by the map on mass airflow input. That's what I said earlier. If you get a poor input, it's going to affect the way the timing is going to affect the transmission, and it's going to affect fuel delivery. Drivability concerns such as hard starting, stalling, surging, spark knot, poor mileage, and excessive emissions can be traced to incorrect map on mass airflow sensors, and basically because it be out of calibration. A problem with the throttle position sensor input may not only cause engine hesitation, but may also affect transmission shift points or fail electronically controlled transmissions. In other words, what I mean by that is, here's the let's say this is a DSO, and here's your TPS. S key on engine off. I'm doing a sweep test on this throttle position sensor. So I go up, I go high, while open throttle, I come down. And that's what you're looking for, a nice clean signal. But how can it affect the transmission shift points? We're talking about up here. If it does this, same signal, it goes up, but it has a glitch in it. And it does this. Then goes back up again and finishes travel. This right here will cause the transmission to shift incorrectly. Because now the PCM / ECM thinks that you just stepped off the gas pedal. You let go of the gas pedal. Alright, and it's going to downshift on the transmission. It's going to shift the transmission incorrectly. Because to the PCM, this signal right here, you just released the gas pedal. But really it's just a glitch. A bad TPS. A failed output actuator, such as an EGR solenoid, may prevent the computer from properly controlling EGR gas flow. The computer may energize the EGR solenoid to allow vacuum to reach the EGR valve, while other systems energize the solenoid to block vacuum to the valve. Basically what this is saying is, it depends how the system is set up. You can allow vacuum to the solenoid or block it to the solenoid. But either way, that you can have a signal to the EGR solenoid, you can have vacuum to the EGR solenoid. But if the solenoid doesn't work, or the EGR valve doesn't work, or the EGR port is plugged up, you're going to have increased emissions, which is NOx. Because remember, the ECM is just giving out an electronic signal to the part. The part will still have to function. The EGR will have to function. The EGR port will have to be cleared. The ECM command is just basically an electrical signal to work. If the part actually works or not, that's another issue. So like on the ASE test, it says the PCM is supplying supplying a ground signal, a post-width modulated signal to the EGR solenoid, but the vehicle still may have high emissions, like high NOx. They give you a couple of choices. If I got power and I got a signal, and the valve not working, I can either have a vacuum related problem, a solenoid problem, an EGR valve problem, or a port related problem. This is what this paragraph is saying. In the first case, if the EGR valve does not receive vacuum, the engine may produce a spark knock, that's pinging. In the second case, if the computer cannot limit the EGR flow, hesitation, surging, and power loss may result. In this case here, some solenoids receive manifold vacuum, but the computer bleeds off the vacuum to control the EGR flow. If it's unable to do that, you'll get too much EGR, and that's when the car starts hesitating, or even it might either cut. How can I say this? You will get too much EGR flow, or the car can either cut off, like you come to a stop sign. All right, the valve might stay up or stay on. So too much EGR flow is a problem, and not enough flow is a problem. Here's the other one: diagnose failures of communication bus line. I think on the whole ASE test, this is the hardest question that they can ask on this bus line, right? These modules typically communicate with one another over a network or data bus. This network prevents the need for handwriting one sensor to several different modules that use data from that sensor. And basically what it is, remember, it's a network. It's communication from module to module. The data bus can be either a one-wire or a two-wire network that connects each module. For tackling any network fault, it's important to refer to the certain information to determine the type of network. They call it topology. All right, there are different types of networks. If one module fails to send needed information over the network, other modules may set a communication failure (DTC) with that module. In other words, it might snitch on the other module. They say, "Hey, we're not receiving a signal from the ABS. We're not receiving a signal from the transmission module. We're not receiving a signal from the instrument panel module." That's what that means. So it is possible for one malfunctioning module to bring down the entire network. That's why sometimes in the diagnostic routine for the modules, it is routinely says that disconnect one module at a time and see if communication comes back. So that one module can actually take out another module. This is generally one of the more difficult problems to diagnose. One symptom of this fault would be no scan tool communication with any module on the network. And basically, you're doing your scan tool, you're doing a system health check and see does it communicate through the modules, through all the modules. Or does one module doesn't communicate, or do they all not communicate? They all don't communicate. That's why you might have one module pulling them all down. When referring to a diagnostic chart for this condition, it is common to unplug each module on a network while checking for scan tool communication normally. Basically, you get your scan tool hooked up and you start unplugging modules. Now, physical damage to the network wiring can also cause the network to fail. These faults occur when the network wiring is open or shorted. Now, let me ask you this. There's two terminal resistors. One might be in the PCM, one might be in the instrument panel. And they're 120K. 120. 120 ohms. On some of the diagnostic schematics, it says the picture ohm meter across two terminals of the DLC. I forgot which two it was. And you expect to see a certain number, to see if the terminating resistors are any good, open or shorted. If they are good, what number are you supposed to see, do you think? And it's in parallel. They're actually in parallel to each other. And when you go across the DLC connector, all the two terminals, You expect to see a certain number. Now, according to Ohm's law, if they're in parallel, what's the number you're supposed to see?
60.
Yes, 60. It's supposed to be 60 ohms. Any other number, that's a problem.
Yeah, if you see 120, it's a problem. One of them is out.
Yes, exactly.
Yeah, 120, one of them is out.
You're exactly right. Now here's another one. The anti-theft system was designed to prevent the vehicle from being started on the event of theft. Many anti-theft systems involve special keys with chips or transponders in the key. This prevents the vehicle from starting when any device other than the expected key attempts to turn the ignition switch. Now I'm pretty sure if I remember correctly, it stops the fuel. It's a fuel and spark when it goes starting. It doesn't affect the starter circuit. I think I remember that correctly. They might ask the question, does it prevent the starter from turning? And I don't think it's the starter, right? Anti-theft is usually on the fuel or spark, not the
Or the
starter
injectors,
circuit.
right?
Huh?
The injectors? Injectors?
Yes, injectors, yes.
I think what it reads is that it doesn't affect the starting circuit.
Yes, it don't affect the starting circuit, correct.
It will affect, however, either the fuel delivery or the spark.
Yes,
That's what it'll disable. I
yes.
mean, meaning the vehicle will still crank. It just
Yeah,
won't start.
exactly. I crank over, but one had no. It still crank. So that's why I said if they give you a question like that for preventing the starter about the anti-theft system. It's not going to affect the starter. Would be the wrong answer. It's going to be fuel or spark, but not the starter circuit. It says other sensors may have sensors in ignition lock cylinder or switches in the door latches to determine tampering. Uh, malfunction A malfunction usually produces the same symptoms. The vehicle either starts and dies or simply does not start at all. Now, performing a voltage drop test on the power circuits and ground circuits. Now, this is important because sometimes they actually question by a circuit. It might be high resistance on the ground circuit or a control circuit. To perform a voltage drop test, the circuit must be energized to ensure the current is flowing. Remember this, you cannot do a voltage drop on a circuit unless the circuit is energized. Anytime you're doing a voltage drop on a circuit, it has to be energized. Without current flow, voltage cannot drop across any other loads in the circuit. Place the leads of the voltmeter at each end of a wire or connector to be tested, or connection to be tested. Now here's what I'm talking about. Let's say we got 12 volts in a circuit. We have a contact here, contact points here, and we got our load device. Then we got ground. Now this load device can be anything. I like to draw a light bulb, just for the hell of it. Here's my contacts. And obviously on a good circuit, when this circuit is energized and these points are closed, this circuit should drop. $12 volts. And the light comes on and it's bright. Now, like I said, I'm using a light bulb. This could be a fuel pump. This is going to be a coil. I'm just using a light bulb because it's easier. All right, and that's a normal circuit. So now this is the voltage drop here. This is the voltage drop. But I can also check the available voltage going to this circuit. Our potential voltage going to that circuit, to that light, to that load. That should be 12. in this circuit. And again, that should be near 1, near 0, indicating a clean circuit, right? Now, let's say we don't have a clean circuit. We have high resistance in the feed side. The contact points are corroded. And for this example, let's say corrosion is 2 ohms. And now remember, I know you cannot measure 2 ohms of resistance across the contact. I'm just doing it for the math. Oh, this is not 2. So this is not going to be 3 amps anymore because I got additional resistance. So I got 2 ohms, 4 ohms, 6 ohms total. I just went down from 3 amps to 2 amps in this circuit. And remember, amperage does the work, so we already know the circuit's not going to work the same because we got less current in the circuit now. But now we need to find a problem. If I do a voltage drop across the contacts to try to find this problem, I'm going to see 2 ohms, 2 amps is a 4 volt drop. So now my load device is 8 volts. 4 ohms, 2 amps is 8 volt drop now. Obviously, this light's not going to work like it's supposed to. And also going to the light would be 8 volts. The ground won't be affected because the problem's on the feed side. So and the reason I'm drawing this is because, think about this. Imagine that this point was a relay going to a fuel pump. Instead of being system voltage, I have 8 volts. Imagine this contact was a relay going to injectors. Instead of being system voltage, I have 8 volts. Obviously, it's not going to work, and field delivery is going to be affected on both cases. Imagine if this point was a connector going to the coil. Instead of getting full system voltage, I have 8 volts. And guess what? At idle, it may work fine. But under load, since it's only 8 volts and less current, that coil may not saturate fully and have a misfire under a load. You see the comparison here I'm trying to do? You understand that? What I'm trying to do here? Now that's the feed side circuit. But guess what? It can work the same problem let's go back. We start the good circuit again. This is a good circuit. Now the same problem is going to happen on the ground circuit. I can have a bad ground here. Okay? And if I can measure the resistance on that ground, it would be 2 ohms. Remember, you can't. I'm just doing the math. I would have the same issue. But this time, let's figure out the math first. I got 4 ohms, 2 ohms. Oops. Right? That's 6. My current will be 2 amps in this circuit. Now the problem would be this. I would have to do a voltage drop here. Let's try to figure this out. Hold on. We erase this. I'm going to erase this. If I got clean contacts now, because the problem's not here anymore and the switch is closed, I'll probably read a tenth of a volt, indicating clean contacts. But here, I'm going to still see 8 volts, indicating the circuit has been robbed of 4 volts. I do a voltage drop on the ground side over here, 2 amps, 4 ohms, it's going to be 4 volts. Like we said earlier with the TPS, it's going to require 4 volts to push the current through a resistor down line, which is this. But now the problem on the feed side circuit, it's on the ground circuit. And you can tell what side the problem's on by doing the voltage drop. But guess what? The part is still affected the same way. The part is being robbed of voltage either on the feed side, we showed you earlier, or the ground side, which I'm showing you now. So it was a fuel pump, injectors, a solenoid. If it robs the circuit of voltage, causes a bad resistance, and you find high resistance by doing a voltage drop, it's going to affect the way the circuit operates. Does that make sense? Any questions on that?
No.
All right. And here's like SAE, I think it's SAE standards of voltage drop. Across the connection, you should have barely any loss. Across a length of wire, maybe 2/10. All depends on how long is the wire also. Across a switch or points, maybe 3/10. And a ground circuit, about 1/10. The ground on the ground or a ground connection, about 1/10. Anything over that, you got high resistance. Up here it says a lower current circuit should have very low voltage drops. Higher current circuits typically allow for a larger voltage drop, up to 5/10, like on the starter cable. And starter cable and the relay contacts together probably like 5/10. Maximum voltage drops across circuit wiring connections and switches. Oh, this is what I just showed you earlier. It was this. All right. Remember, the reason you're doing the voltage drop to check for resistance. And resistance will affect the way a circuit works. Electronic systems operate with low voltage and very low current. A clean ground connection with minimum voltage drop is essential. To measure the voltage drop across the complete ground side of a circuit, connect the voltmeter negatively directly to the negative battery terminal. Then probe with or connect the positive lead to the ground circuit of the system being tested. It's basically what I just showed you in that drawing. And this picture is showing how you do a voltage drop. Okay? Like I did earlier. Let me see. Oh, I erased it. What I was doing here on this page earlier is I had the red lead connected to the circuit. Let me show it again. What I'm trying to say on this is this. Going back to this. What the picture is saying, that slide is saying, is this. Here's the voltmeter. Here's the red lead. And it's ground. And what it's saying is the red lead go to the most positive side of the circuit. The ground lead, I'll make the ground blue, goes to the least positive side of the circuit. Alright, that's what it's saying. The red lead goes to the most positive side because that's the voltage, that's the battery. And the negative lead goes to the least positive side. Since on the other side of the switch, that would be the least positive side because it's going through the switch. The same thing here. The same exact thing up here across the load. The positive lead, the red lead goes to the most positive side of the circuit. Let me erase this. I don't want to confuse you. And a, oops, crap. What's going on here? And a black lead go to the least positive side of the circuit. See here, the red lead. This is the hot side, so the red lead goes there. This is the ground side. The black lead goes there. The last one is saying I'm doing voltage drop on the ground side. Oops. The red lead goes here. And that's supposed to drop on the ground side. The red lead goes here to the ground terminal. The black lead goes to either to the ground over here or back to the battery ground or the frame of the car. Let's say it's the frame over here. So it's ground to ground. It's supposed to drop on the ground side. The red lead goes to the ground wire here. The black lead goes to the frame of the car or back to the battery. It's usually going to be the frame of the car though, because that goes to the battery. And basically that's what that slide was saying. How you do a voltage drop. A voltage drop of the ground circuit should not exceed a tenth of a volt. Now remember this. Now, this is going to be important too. Anything higher than this, excluding system voltage, you have high resistance in the circuit on the ground side. If it reads system voltage, you have no ground. You get that? Anything higher than this number here on the ground side of the computer circuit, you have resistance on the ground circuit. Excluding system voltage. If it reads system voltage on the ground side, it means you have no ground. You don't have a ground at all. Okay? You have an open ground. So anything higher than 0.1, you got resistance on the ground side of that circuit. If you got system voltage, if you have system voltage, you don't have a ground. You have an open circuit on the ground side. Sometimes that's good, sometimes that's bad. Because keep in mind, really quick here, here's a PCM. Right? I keep saying PCM. PCM, ECM. Right. Here's the load device. Here's the source voltage, I mean. Here's my load. Guess what? If this is source voltage going to the load, it's going to the load, that's source voltage. On this side, no matter what, that's the ground side. It has to be. Even though you don't see the ground symbol like this, even though you don't see that ground symbol, you have to know if this is source voltage and that's the load, this has to be the ground side. Now, the reason I'm saying that is because I said earlier, if this is power control, this will be a pull down. If this is a pull down circuit, meaning the voltage being pulled down, if I put a voltmeter on this circuit, going off what I just told you earlier, if this circuit is not activated, I'm going to see what? What do you think I should see right here? Say it again.
If it's
If it's not activated, what kind of voltage should I see on that line right there?
12 volts.
You're going to see 12 volts, exactly. Now, again, that's an open ground circuit. Like I said earlier, that's an open ground. 12 here and 12 here, you have no ground. But that's a good situation now. Now, when the PCM controls this load and turn it on, that 12 volts should drop to somewhere near 0.1. Since it's a driver, it might go to 0.75. That should be somewhere close to 0.1. A transistor might be a little higher, but it should drop. Now, when it drops like that, it says 0.1, it drops. That means this circuit is now energized, engaged. That load should work. Now, let's switch it around. Let's say that they ask you a question on the ASE test that my ground circuit, this circuit is being energized. I'm reading 12 volts on this line. With it energized, your load does not come on. What's the problem?
It's reading 12 there.
Say it again.
It's reading 12 at the.
Yes, reading 12 right here. But the question is, it says the circuit's being energized. My load does not work. This load device, whatever this load may be,
You don't have a ground.
you don't have a ground. That's why I said to back up to this, right? 0.1 is a given number. On a transistor, it might be a little higher, but let's go with 0.1 right now. Anything higher than 0.1 on the ground side, you got resistance, except you got system voltage. If you got system voltage, we're down here now. It means you have no ground at all. So using that same theory down here, you can use it in your diagnostics. If this circuit is energized, and I'm reading 12 volts on this line right here that goes into the ECM, the transistor is not working for some reason. If it goes down to 0.1 and it's energized and the circuit don't work, the load device is not working. You get it? Now let's give you one more example before we go. Let me give you one more example. Let's say this. Oops. Do this. Let me show you. Now let's do this now. Let's say this is a fuel pump. No, a light bulb, it don't matter. Let's go with this analogy here. On the ground side, we gotta see 0.1. Here, we see 12. Here, we see 2 volts. We see 2 volts on here, on this side right here. Is that a problem?
2 volts there.
I can't hear you. What you say?
Oh, I was saying there's 2 volts there at the reading.
Yes, 2 volts here. Is that a problem or is that good? Or is that good?
No, that's a problem.
Exactly, that's a problem. Right? That's a problem. That goes over this number here.
Yeah.
Right? So that's going to affect the way this circuit works. All right, that'll be it for tonight.